So yesterday we talked about transformations of functions, and we said that if we've got some function we want to graph, we always want to think about it in terms of how we would transform a parent graph, right? The most basic, boring version of a graph. And we identified really just 3 transformations. That's all we needed to do transformations of these graphs, A, H, and K. Remind me, what was A? What did that stand for? Vertical dilation factor. And we want to say factor because that reminds us we're multiplying. What's H represent?
H is
Horizontal translation. K is vertical translation. Okay, good. So for this function here, we're going to graph the function f of x equals 2/5 times the absolute value of x. I guess first of all, what is my parent graph? Absolute value of x. How come? How do you get that? Okay, because if we were to like erase all of the values of the parameters, the numbers that are not an integral part of the function from our transformed function, what we end up with is the vanilla parent graph, right? So it'd be the absolute value of x. Good. So what is the value of a then for this function? 2/5. Okay, so a is 2/5, pretty obviously. Show me with your hands, everybody, what's the value of h? Okay, so I'm seeing a couple, is it 1 or 0? I'm seeing 2 different values. It's 0. Yeah, it's 0. How come? Because remember, h is the number that's being subtracted from x inside the function, which would mean in this case inside the absolute value bars, right? Well, what number is being subtracted from x in there? 0, because nothing shows up. What's k? 0, because nothing is being added to the function outside of the absolute value bars. Okay, so then the only thing we have to do is dilate this thing vertically. How are we going to do that? The way we talked about yesterday, I'll add another technique today that always works, but the way we did yesterday is the most efficient way of doing this. What does a vertical dilation factor of 2/5 imply about the shape of this graph? I'm going to multiply 2/5 times what? No, okay, it's not the slope. Now, you guys you're really smart, and so you see patterns easily. And you see a pattern here that the slope is 2/5, right? Well, that's what it's going to be when I graph this thing. The slope is going to be 2/5. You already see that. You probably noticed that yesterday with these absolute value graphs. Don't depend on that. Erase that one from your mind because that one is not useful. That is a specific example that applies to only absolute value graphs. It will not apply to other graphs, and most of the time we're going to deal with other graphs in the future. So we got to think about this differently in a more general way that always works. What am I multiplying the 2/5 by? True, but if I want to graph this thing, I need to plot some points. Like, let's go ahead, if we're going to graph f of x, what's one point that we automatically know is going to be on our graph without even thinking about it? Yeah, okay, whatever the vertex of the absolute value graph is, we haven't translated anywhere, so the vertex is going to stay at the same place because when I dilate this thing vertically, that's the point that's fixed, that we're tacking to the xy plane, and all the other points are being stretched or compressed from that point, right? You get my idea? You see the important point there that you have to recognize, and you got that. That's a point that we already know is going to be there. How many other points do I really need to graph this thing? I just need one, right? I only need one because we can take advantage of some good symmetry here, right? We know we've got, I think we kind of alluded to this yesterday, right? We've got this folding or line symmetry about the vertical line through the vertex, which we just call the axis of symmetry, honestly, right? That's what that is. So we just need one point, and then we could connect and extend a ray to create the right leg and fold it over the axis of symmetry to create the left leg. We just need one. How are we going to get that point, though? How are we going to use the vertical dilation factor to get that one point that we need? What am I multiplying? The question is, what am I multiplying by 2/5 to get that point? The y-coordinates, the heights of the function, right? So what do we mean by that again, right? If an ant travels 1 to the right from the vertex, On the parent graph, what is the height going to be there? How high does he have to go up? 1, okay? So the dilated height is going to be what we get when we multiply the parent height or the normal height by the dilation factor. Can you predict for me right now, is this going to stretch or compress the graph vertically? It's going to compress. How come? Less than 1. It's a fraction less than 1. Okay. So we know it's going to compress it. So for example, if I went to the right by 1, I would go up, instead of going up 1, how far up would I go? 2/5, because I multiply the normal height of 1 by my dilation factor of 2/5. That would put me somewhere like right in there. That's not a very convenient place. Can I find a more convenient height to use than a height of 1? I could use a height of 2. If I go over 2, I would normally go up 2. Well, I could multiply 2 times my dilation factor of 2/5, and I would get 4/5. That's still not super convenient. 5 would be good, right? What if I went over 5? If I travel over 5 from the vertex, my parent height is 5, but 5 times 2/5 is what? Is 2. Okay, that's kind of useful because now I could just travel, I could travel up 5 times 2/5, which is 2, to identify another point that we could use. That's all I need. You see what I'm saying? So if we're using that stretch or compression technique, well, we just want to find a height that's compatible with our fractional dilation factor. In other words, it needs to be some multiple of 5, so that when I multiply it by 2/5, I get an integer. Right? Everybody see that? Okay. So then we would just connect and extend. There's the left leg. I'll just reflect this point over our axis of symmetry over to there. And now I got another one. Okay, give me thumbs on that. Does that make sense, how we're doing that? Okay. All right, let's, just quick reminder here. What are the values for this particular function? What is my parent graph, parent function, first of all? Absolute value of x. If I were to erase all the all the numbers that are not a part of the function, you know, part of the, you see what I'm saying? Like what I mean by that is if I had something like f of x equals x squared, can I erase the 2? No, that's an exponent, right? That's part of the function. That's not a parameter. That has to be there for my function. But all the other numbers are just parameters. If I erase the parameters, I get absolute value of x. So what are my values of a, h, and k? Everybody, what's a? What's h? 8. Positive 8. What's k? Okay, good. Okay, now what I want to do now is I want to just show you something really cool that you're now able to do. We don't even have to necessarily know what the kind of function is. We don't have to even be familiar with the function, and we can still make predictions about what the transformation is going to be. This is an easy one. What's the parent graph or the parent function here? This is a warm-up. Absolute value of x, right? We've already kind of looked at that. 8a is what? 3. H is? K is? Okay. Take a look at that one now. Don't say anything yet. Think about it. Discuss it for a second if you need to. What's the parent function here? Okay, is it x plus 1 squared or x squared? The plus 1, can anybody tell me what's the value of h going to be? Can you make a prediction? Okay. H is going to be -1. So that 1 up there, I could erase that if I'm trying to find the parent graph. That's a parameter. So yeah, the parent graph is x squared. The parent function is x squared. I'm tweaking an x squared graph to get this. What's A? Okay, good, because that's what's being multiplied out front. What's K? 0. Okay, give me 1 to 5 on that, everybody. How are we doing? Okay, let's do some more. Some more of those. Okay, take a second and think about that one. Again, if I were to erase all the parameters here, what's the most basic function I could distill this down to? Square root of x, yeah. Okay, now, what's the value of h? Negative 4. Yeah, but give me 1 to 5 on that. Everybody good with that? Why it's negative and not positive? Right? How come it's negative and not positive? Okay, yeah, because I'd have to subtract from x a negative 4 to get x plus 4. What's k? Okay. Show me with your fingers. What's a? Okay, so which one is it, 0 or 1? It's got to be 1 because it's a coefficient. That's different than the previous examples. Like here, k is 0 because I'm adding nothing to this, right? When a term doesn't show up, it must be 0. If an invisible term is a 0, but an invisible factor has to be a 1, right? If I multiplied that thing by 0, it would go away. Okay, so it has to be a 1. Okay, you don't even know what that is, but I'm going to see if you can tell me. This is really tricky. See if you can tell me what the parent function is there, and you've probably never even seen this before. You don't even probably know how to say it, but maybe you can tell me how to write it at least. Anyone want to take a stab at that, what the parent graph is? How would I write it? ln of x. Okay, that's natural log. What that really means is natural log of x. You haven't seen that yet. That'll be something we'll maybe touch on a little bit at the end of the year this year. For sure, you'll see it a lot next year and a ton in calculus. So it's a natural log function. You don't even know what that thing looks like, but you could tell me how it's transformed here. What's the vertical dilation factor? 1/4. What's h? 0. So it's not translated at all. What's k? What's that mean? Pushing it up 5 on the graph, right? So even though we don't know what it looks like, we know what we would do to the graph if we did know what it looks like to graph it, right? That's kind of cool. Okay, last one. Really tricky one. Take a second, talk it over, discuss with your neighbor for a second, see if you can tell me what the parent graph is here. Anyone want to take a guess here? What do you think, Benjamin? Yeah, it's 2 to the x. So this is what we would call a base 2 exponential function. Okay, that's weird. What is the inside of this function? And I'll give you a hint. The inside of a function is where you would be plugging in values of x when you evaluate it. So where is it? What's the inside of this function? In the exponent, yeah. That's the inside, right? Okay, so then what's the value of h? It's 12, right? Because 12 is the value of x the number that's being subtracted from x inside the function, right? In the exponent, I'm subtracting 12 from x, so h must be 12. What's k? Negative pi, because that's the number that's being added outside the function. And what's a? 3. You got it. So without even knowing anything about this function, you do know how we transformed it there. Okay? All right, so if we were to follow, now you guys it's been drilled into your head that we simplify things by using PEMDAS, right? So if we followed PEMDAS, what would be the order of the transformations we would have to do to this parent function? So parentheses first, right? So I'd take care of the first thing we would do is the horizontal dilation horizontal dilation, h, right? That'd be step 1. So parentheses, right? What would be next? We'll say it again. Vertical dilate. Okay, so the A, we got to multiply next. So we get, next would be vertically dilate this thing, right? Apply the dilation factor, so that would be multiplication. And what would come last? Yeah, addition. So we do the K, which would be the vertical translation, right? Okay. That is not the most convenient way to do it. Okay, I'm going to show you a better way. The good news is you do not have to follow PEMDAS here. This is important. All of those transformations are independent of each other. Okay, you can do them in any order, which is really nice. What that allows us to do is something really cool. It allows us to, when we're applying the translations, which we would do first, let me ask you something here. Like if I do an example, I want to go back to one for just a second. Have we moved one of these yet? Actually, let's scoot ahead for just a second. Like what about this one? If I want to transform this function, this absolute value function, what are the values of A, H, and K real quick? What's A? 3. What's H? 5. What's K? Okay, good. So now look what happens here when I'm going to do my translations first. I'm going to take this guy and I'm going to move him horizontally 5 to the right, and I'm going to move him vertically 6 down. How many points are on an absolute value graph? How many points are contained in that graph? I mean, how many total points? In fact, how many? Those arrows mean it goes forever. So how many points are contained there? If I wanted to build this, there's an infinite number of points, right? When I smash all those infinite points together, they end up creating the shape of this graph. How many points are there on this graph between 0, 0, and 1, 1? An infinite number, because I could keep zooming in and in and in as far as I want to go, and there's never going to be a shortage of points that I could jam into that one little space. I can zoom in infinitely far, and there's never going to be a place where I'm going to run out of numbers to create coordinates to fill in points, because numbers can get as small as you want them to be. They can get as close to 0 or as close to 1, or I can get, you get my point? Okay, so when I scoot this thing, when I translate it, I am literally translating an infinite number of points from my parent graph position to my translated position. Okay. Most of those, it's kind of hard to predict. You have to do a little bit of thinking to predict, for example, where that point is going to end up, because those are sort of complicated coordinates. But there's one specific coordinate that you automatically know without even thinking about it what the coordinates are of the point where it ends up after translation. Which one is that? The vertex, right? How come it's so easy to predict? I can predict right away that the coordinates of the vertex are going to be 5, negative, oh, I didn't draw that right, did I? Whoops, I messed up. I gotta go down one more, don't I? I can predict right away, without even thinking about it, that the coordinates of the vertex are going to be 5, negative 6. How? Why is it so easy to predict what those are going to be? I slid 5 to the right and down 6. Why is it so easy to predict where the vertex ends up? Because it started at 0, 0, right? So 0 plus 5 is 5. 0 minus 6 is negative 6. So look what we can do here then. If we're dealing with a function that has a vertex at the origin, which most of our parent graphs are going to do, they're either going to have a vertex or they're going to have an interesting point that is at the origin for virtually every parent graph we'll ever work with. So I automatically know that the values of H and K are going to be the coordinates of the vertex after I translate it. This even works for some really bizarre graphs. Like I'm going to give you an example here of a really strange one. What if I did something like, I'm going to do an inverse, or sorry, a reciprocal function. So if I take the function p of x equals 1 over x, this is what it looks like. Okay, what is kind of the middle point of this, the point that about which this function has some symmetry? Because it's got to be, if I look back at the vertex of a function, these interesting functions, usually it's going to be a place of symmetry, like 0, 0 is a point of symmetry because that's where the line of symmetry intersects the absolute value graph. Okay, what about this one? What's the point of symmetry on this function? 0, 0. You know, what kind of symmetry is that? It's actually not because it's folding symmetry, because that's not really a good line of symmetry. A diagonal line of symmetry is not very useful to us. We can use it sometimes, but there's a different kind of symmetry. I'm going to do something else. Just want to remind you about symmetry. These are kind of fun when we just go on these, you go on some tangents sometimes. You get really interesting in math. So you guys have talked about symmetry and geometry quite a bit. What's one type of symmetry that square has? Okay, it has some line symmetry about that vertical line. About a horizontal line, it has line symmetry. Any other lines? There are diagonals too, right? Although it has line symmetry about all those places. Okay, that's good. Yeah, you found a bunch. That's it for line symmetry. Any other types of symmetry that thing has? And why does it have line symmetry about this line? Okay, because if I fold it, or if I reflect it over that line, doesn't it just reflect onto itself? Right? Okay, so that's what symmetry means. I can apply some symmetry to an object and it doesn't change. Therefore, it has that type of symmetry. I could reflect this whole thing over any of those lines and it's going to end up being itself, right? What else could I do? What other kinds of symmetry? What if it's not line or reflective symmetry? What is it again?
Radial symmetry.
What do you mean by that?
Or like if you rotate something around a point.
Okay, rotational symmetry, exactly. What if I do this? Hey, what do you know? Lines up. Agreed? So we can also have things like rotational symmetry, right? It doesn't have to be line symmetry. It doesn't have to be either one of those things. In math, a lot of times, or in physics, we deal with other bizarre kinds of symmetry. Okay, imagine this. Take a ball. Just imagine this situation. I got a ball. You're going to film this with a video camera. Take a ball. I throw it up in the air, and I catch it. Okay, we're going to watch the video. Pretend I show you a video. You don't see my hand. You just see the ball rising up and falling back down. Okay, is the video I'm showing you, let's pretend it takes 4 seconds for the ball to go up and down. 2 seconds to go up and 2 seconds to come down. I'm going to show you a 4-second video. Is the video a 4-second video of the ball going up and coming down, or is it a 2-second video that's shown in reverse for the second half of what you see? Right? Pretend I only filmed it for 2 seconds, and then I reverse that video and I stitch those two things together. Could you tell the difference by watching the video? You couldn't, could you? You wouldn't know which one it was. It'd be impossible to tell. So because it's impossible to tell, that must mean that there's a symmetry acting there, and there's time symmetry. The path of the ball is time symmetric about the point where it hits the apex. If I go forward in time from there, it falls down to my hand. If I go backwards in time from there, it falls down to my hand. They're identical, right? So we can take advantage of that in physics all the time. That's something we do. In fact, most of the physics that you learn as an undergraduate in college, if you study physics, most of it is time invariant. Classical physics is all time invariant. You can run it forward or backward equally well, which is pretty bizarre in some ways. Okay, so different kinds of symmetry. So what is the symmetry here then? It's rotational symmetry about the origin. If I put a tack in the origin and I spin this thing 180 degrees, doesn't it end up looking just like that? Everybody agree? Okay. So bizarrely, that is the point that we want to track. Like if I were going to translate this thing somewhere, you guys tell me real quick. I'm going to draw another version of this, and I want you to tell me, without even thinking about it, what's H? I'll give you a hint. What's H? Yeah, K is, because those are the coordinates of my special point, the point of symmetry that started at the origin, right? Okay, you get that? That's huge. What that does for us is it allows us to use what's called a vertex method or a vertex form of lots of different functions. Rather than doing two steps of shifting our parent graph horizontally by H and vertically by K, well, we can kill two birds with one stone, and we just place the vertex at the coordinates HK. Does that make sense? So we locate the vertex, and then we're just going to dilate the function from that location. Okay, that's pretty good. Do you guys remember talking in Algebra 1? I'm sure you would have talked about this when you dealt with quadratic functions. There was standard form of a quadratic function. What was the other form you probably talked about? Do you remember? It's been a while. Maybe you did. Maybe you didn't do this. Did you ever talk about vertex form? Maybe you mentioned it at least. Okay, we're going to talk about it a lot this year. So if you talked about vertex form of a quadratic function, okay, it was this. It was y equals a times the quantity x minus h squared plus k. I promise you. What did you know h and k represented? Well, at the time, you didn't know anything about transformations, right? You just knew that it was the coordinates of the vertex, maybe, right, when you talked about it. You didn't have to know anything about transformations. What are they, though? Well, those, of course, if we think of the parent form of the graph of a parent function, darn it, for a parabola, if I graph y equals x squared, where does the vertex start? 0, 0. So vertex form, really, we're just relocating the vertex by translating it, but we don't even have to think about it as a translation. We just now know the coordinates of the vertex. Okay? So that expedites the process a little bit. So when we're trying to graph this f of x, well, we just automatically know we start at 5, -6, because that's where the vertex is, right? Then what? Well, now we have to dilate this thing. Okay, there's a couple ways we can do that. One way we can do it is we could do it using a t-table. If you don't want to do, think about how you're going to stretch this thing about a convenient point, that's the way I prefer to do it because I think it's quicker. But you don't have to. You can always just make a t-table. What's one point that we already know sits on that graph before we do any translation? 5, 6. Yeah, we know the coordinates of the vertex, right? The vertex has coordinates 5, negative 6. So those are already points that we know sit in our t-table. Well, how do you use a t-table? Remember how that works? From back in the day? There's my function. How do I use a t-table? I plug in x values and calculate y values, don't I? Right? So let's try it. What's another x value I could plug in? I mean, I could plug in lots of them. I could plug in like 0. If I plug 0 in, here I've got the equation y equals 3 times the absolute value of x minus 5 minus 6. If I plug 0 in, what am I going to get back? 0 minus 5 is negative 5 times 3, or absolute value of negative 5 is 5 times 3, 15 minus 6, so 0, 9. There's a point, right? I can do that. Probably the most convenient points for us are going to be ones close to the vertex most of the time. If we're dealing with a function like this is a pretty tame function because there are no exponents in it, but if it were quadratic or cubic or something, then if I get very far away from the vertex, this thing is going to tend to grow really, really big or really small, right? I mean, really big in the positive or negative direction. So usually we want to pick values close to the vertex. So I would probably pick something like 6. If I plug 6 in, 6 minus 5 is 1. Absolute value of 1 is, times 3 is, minus 6 is, over 6, down 3. All it takes is 1 point, because I already know that that point stays the same. There's my graph. Everybody see that? You can always just build a t-table and pick some convenient points. Okay, we can also do it by stretching though, by stretching a point. So normally, if we know our parent graph has a vertex, we already said it has a vertex at 5, negative 6. Normally I would go over 1 and up 1, right? Everybody agree? Okay. To find the dilated height, I'm just going to multiply my normal parent height by 3. Okay? So 3 times 1 equals 3. So instead of going over 1 and up 1, I'm going to go over 1 and up 1 times 3. I'm going to go up 3 to this point right there. Everybody see that? And so I'm just going to take this thing. Well, I guess I can't. I thought I could. No, never mind. I'm just going to stretch my graph up through that point. Okay? How about one like that? I want to graph f of x. What do I do first? Where's the vertex going to be? 0, 0. Okay, but where's it going to be? What's it going to be? Negative 6, negative 3, right? Right. Because h is negative 6. Okay, so my vertex is going to have coordinates negative 6, negative 3. So I take this guy, negative 6, negative 3. Okay, good. Now what? Okay, so what's that going to do? Okay, and tell me how to get to another point. I'm going to go over 1 and up how far?
Down 2.
Okay, up negative 2.
Yeah, up negative 2.
Right? How come? Because a is negative 2, right? So what's that tell me? That tells me that 1 times negative 2 equals negative 2. So instead of going up by 1, we're going to go up by -2 and get there. Good. And I could just use a t-table also, right? I know we already have the point -6, 3, so let's pick a point around -6, like -7. If I plug -7 in, -7 plus 6 is -1, right? Absolute value of -1, 1 times -2, -2 minus 3. There you go, right? So -7, I should have picked -5, shouldn't I? -7, -5. So I go down to there, reflect it over, and I get my points with the t-table. All right. Okay, what about that guy? That's a little trickier. Where's my vertex?
-1, +2.
-1, 2. Good. So we locate the vertex, -1, +2. What's A? Okay. So how am I going to find another point? My parent graph would normally, what would be a convenient height to multiply by -4/3? 3. Okay, but to have a height of 3, how far over would I have to go from the vertex? On my parent graph. Like, think about absolute value graph. Just looks like, whoops, just looks like this, doesn't it? How far to get a height of 3, how far over do I have to go? 3, right? So over 3, up 3. Okay, we'll finish this last little bit tomorrow, and then we just have like one more problem, and then you guys can work all day.